Yeah, this thing. Sure. Okay, so our sample size, remember we had 6 students. All right, degrees of freedom equals 6 minus 2. We now have 2 degrees of freedom, where we have n minus 2 to account for the 2 unknown variables. The intercept and the sample and the slope. Intercept and the slope. So 4 degrees of freedom. So you're going to look on the t distribution, 4 degrees of freedom, and you know that you're going to have 2.5% in either tail. So you're going to move your finger to the 2.025, and it's going to say 2.776. All right. So same thing with the sample slope. So we, based on our hard work, we have calculated a sample slope. But that's just a sample, based on 6 points. So we need a confidence interval. We're going to take that slope and we're going to go plus or minus some number of standard errors. How many standard errors? Depends on how confident you want to be. How are you going to determine how many standard errors? Well, you're going to need to use the t distribution because now you have more unknown factors. You have 2 unknown factors, so you're going to take n minus 2, that's going to be your degrees of freedom. You're going to decide how confident you are, or want to be, and you're going to crunch out your confidence interval, and you're going to stand up and you're going to say, I'm 99% confident that the true population slope is between this number and this number. All right. Now that is going to bring us to the key hypothesis test. What did I say is the key hypothesis test in regression analysis? What is the key question when all's said and done? Has nothing to do with statistics, right? All right, the key question.
Do we have a slope of 0?
Do we have a slope of 0? All right, we've done some work. We took 6 students, a good sample, random sample of 6 students, and we calculated this estimated regression equation. And we're wondering, even though we see a positive slope in this sample data, can we really infer that the true population slope is something other than 0? Adonis.
You asked about this, right?
Yeah.
Fail to reject or reject. So we know for sure that we reject something, certainly. And fail to reject would be that it's a possibility, it might be true.
Yeah, so what is our null hypothesis, Adonis?
That he fell. It fell?
Can I just read this? What does that say?
Oh, I can't read.
Is the slope 0? Is this
Yeah, you're right. But can somebody just read this to me?
Population slope is equal to 0.
Population slope equals 0. So this
that is
Greek letter B is the true population slope. So we have this, but this is just the sample slope. The key question is the true population slope equal to 0? We're going to make that our null hypothesis, and we're going to assume that's true unless we have overwhelming evidence to the contrary. If we have overwhelming evidence to the contrary, reject this and assume the alternative hypothesis. The true population slope does not equal 0. Then we've got something useful. And we've got overwhelming evidence to support that. Because if the true population slope is 0, if it's just a straight line, again, it doesn't matter, it may not matter how much time you spend studying. It may not affect your grade. We can't say conclusively that there's a relationship between those two if we have a line of 0, a slope of 0. All right. So, if the slope is 0, the variation in y is unconnected to the variation in x. Now, what else does that say there? On the other? I can't read that. It's on the. What does it say below?
If b is not 0, at least some of the variance in y can be explained by y connecting to x.
Yes, if b is not 0, at least some of the variation can be explained with your regression equation. Alright, so our test statistic for our key hypothesis test is this. Now we're using the t-distribution, not the z-distribution. Use the t-distribution with n minus 2 degrees of freedom. This little b is our sample slope. We want to know how different that is from 0. So we take our sample slope minus 0. More importantly, we want to know how many standard errors of difference that is. If it's 5 standard errors difference from 0, then we're like, wow, that is very significant. It is so unlikely that that happened by random chance, then in fact there is a relationship that's making the data look the way it is. If that's like 1 standard deviation of difference, then we might say, well, you know, it's just those 6 students. We got a weird sample. It turned out that the one who studied a lot just happened to be good at statistics. And it didn't necessarily have anything to do with the correlation between those 2 variables. So we want the difference between our sample slope and 0. More importantly, we want to know how many standard errors of difference it is. Okay. And then we're going to set up a hypothesis test. This is sampling distribution of the sample slope. Null hypothesis says the mean of this slope is 0. Alright, the true population slope is 0. If it's close to 0, we're like, okay, well that's just sample data. The true population slope still could be 0. If it's really far away from 0, we're going to start to get suspicious, so to speak, and say we may be able to reject the null hypothesis. If the test statistic ends up in the upper tail or the lower tail, we're going to say, yeah, that is overwhelming evidence to the contrary. That falls in our rejection region. What are the critical values? Well, based on a t distribution with n minus 2 degrees of freedom. So suppose we have a significance level of 5%. What's significance level again?
2.5.
That's right, yeah. Well, 2.5 in each tail. Significance level is our threshold for what we're willing to believe.
Okay.
Our definition of unlikely. So anything less likely to happen than 5%, we're going to say that's conclusive evidence to the contrary. So if we have a significance level of 5%, we have 2.5% in each tail. And suppose we have a sample of size 6. So 6 minus 2, 4 degrees of freedom. 2.5% in either tail. What's our critical value upper? It's the same as our confidence interval, 2.776 and minus 2.776. So, we're going to look at this t-stat. If our sample slope is more than 2.776 standard deviations above 0, then we're going to say we have something significant. And the way we're going to say that is we reject the null, which says we don't have something significant. If it's less than negative 2.77, we're going to say, yes, we have something significant, and it's a negative relationship. Publish that in the Journal of Education, right? I found a statistically significant negative relationship between the hours you spend studying and your statistics grade. That's what you do, right? If you had a hypothesis test that passed, you could say, I proved it. And that's how people prove stuff with a hypothesis test. They say, I have overwhelming evidence that the more you study, the lower your grade will be. I guarantee you, if you found that, you'd publish that somewhere. Go ahead.
So can't you determine the same thing by looking at the value of r squared? So if r squared is really close to 1, or you could determine a value?
No, you cannot. You cannot. And here's the thing. You could explain a small percentage of the variation, but that could still be very significant. So look at this, for example. Our first, good question though, Ron. This is the whole population of every statistics student, and we had their study time and their grade. Now you can see that this line of best fit does not hit each person perfectly, right? So what that means is, by definition, there's a lot of unexplained variation. So we might have, looking at this, you might say there's a low R squared. Are you with me there? Because there's a lot of unexplained variation. But here's the thing, can you clearly say that there is a trend? That there is the line of best fit is upward sloping?
Yeah.
Can you clearly say that it is not zero?
Yeah, because the zero, the bubbles is another.
Yes. So that is a statistically significant relationship. So that maybe 40% that we're able to explain is very valuable, and we can say that in fact there is a relationship there. But there's still 60%, which other factors, influence. Whether or not you took statistics as an undergrad, whether or not you have a job, are you under stress, do you like your professor, all those things. Does that make sense? Great. All right, good question though. All right, so what does it mean if we're able to reject the null hypothesis that the slope is equal to 0? We can say there's a significant relationship between the two variables. Now remember at the beginning I said it does not by itself prove cause and effect. Just because we can say there's an upward sloping line in the whole population, that doesn't mean that studying more is the cause of a higher grade. It probably means that. We would use some logic to try to think it through and try to think about how strong our case is, think about if there's anything we're forgetting, and then we, with some careful language, just to make sure no smart aleck in the room can say correlation doesn't mean causation, we would present our case that we think it does cause a higher grade. All right.
Yeah, because my
Great.
son don't have to study for math and he passes, he doesn't study for stuff.
Some people don't need to study at all, so they have no study time, and they have a good grade. Some people study forever and fail the class, right?
Yeah, I understand.
Not my class, I hope.
No.
Anybody who studies forever,
Why is that?
they shouldn't fail. Okay,
I understand it.
we've got some homework instructions which I'll go over later. The good news for the homework this week is I've only asked you to do a few problems. I think maybe 6 or 7 problems. And I've given you some of the background for each of them. Remember how I said your textbook actually wants you to calculate the sample slope
Yeah,
and the sample intercept?
yeah.
You don't have to do that, don't worry about it. Just once you've done that, I've given you this information, and we'll do things like the key hypothesis test and confidence intervals. Let's now look at our Excel printout. Unless we want to break now.
Yeah, it's 7:45.
Great. All right, let's come back at 8
So I didn't
p.m.
have my coffee.
Yeah, let's come back at 8 p.m. and we'll start looking at the Excel printout. Go. All right. Well done.
If I need to ever use a certificate, I will hire someone that has been trained and they can do that. The way that's really when we're gonna use it in real life. You wanna slit my wrist? I don't care, like. Wait, it is a message.
Oh, we walking out?
It's cold.
Alright, so you
gotta walk out.
Standard deviation sampling distribution.
You told me to walk out.
I get
Okay. Oh, it is.
That's your answer?
That's your like motion.
That's what I was saying. No, I did the math and I put it in. I have looked at it. I was walking to one
It's like a different
No, I'm fine.
So,
Okay. I've been okay with
we'll reset this,
I just worry like, let's see.
and you just input your actual.
Because I look at it on an
Say, please remember 5 per day, please remember to reset to base 5, and then just input the actual.
Yeah, if he doesn't know, we're going week by week. But I think, well, I did this right now, I remember. Right. But I think we have problems, I think
Your critical values.
it is. So give me a question
What, tell me what
the
you're
first
gonna.
day, and I'm like,
Tell me it's an
I'm there yet.
We spent some time going over this.
Well, after this.
Get that, I said, let me ask, okay,
Yeah, it's like the part.
So I just wanted to show
I'm looking at grades, but this is how my chapter 9. I think the most of them.
Okay, well, yeah, seems like as long as you're keep up the good work.
You did all this. Exactly. Nobody said Excel, you can see the thing with them.
No, they were all the Z. Yeah, they were not.
There's Z, because there's no,
There was no T.
no, he calls it test set.
It's a test set, but it's
Yeah.
So which one is the right one?
I just got this one.
Well, this one's that.
I'm just
I
down.
told them this one, and I told them it's all human error.
I'm just
I
checking.
was looking at
I'm going to think that that's what I'm saying.
I would just start with it, because I was in the science. It's kind of around that old, like, learning, you know,
Going to pee?
Now, I didn't walk on, I didn't walk on Sunday. Just now. I'm gonna send it to you. It's in my email. Let me see. I have it in my thing, I'll send it to you right now.
Or the other one.
This group
That's okay. I have the regular, that comes with that one? Oh, like, I get it from AJ?
And then, I mean,
No, I have the regular one with the almonds, the apple, the almonds, the raisins. Then I bought a thing of fresh one. From Shining Top and over here.
What I did the last
You don't have. Oh, you got no? Me, no. Yeah, but all the tests, yeah, but all the tests and everything.
I did it. That's what I said. You did it with the test, quiz.
Did the exercise?
Did you exercise Excel?
Where you
You did the quiz, right?
I'm sorry.
I did the quiz, that's what I said.
When you
And I did what I said. Excel.
I said,
Well, that's good. I did it before I signed on, I mean, December 23rd. And how we doing? I did day one day. Which was, I was home that Saturday, the 23rd. And I was by myself. And I said, by yourself. No, you know why I said by myself? Because I have a big floor. My kids will be on the second floor. And I'll be by myself. In my room.
y'all women can.
Yes, and I got a rent too. And then they do a full of second floor.
Drown them out, huh?
It'll come bother me. So that's it.
No, that's nice.
And I was up from like 7, no, 4 because I'm up early. And I was just doing it. That's what I'm doing.
He's not even asking a question.
This is the first class that I just took to graph.
But
I have
to print them out.
You signed this? Let me know if you signed it. What? I said, you still signed it.
Oh, yeah.
Oh, you still signed it. I
Oh, no, I'm not. Nobody took it off. So we got the, class, and stuff. He must do it,
But I see class. So I sent him a picture of the formula. And I'm going to use.
this is the only class you
Work it out. So after the class that we gave our kids, because he didn't have it. He was like.
International timing? Or you did the timing? So you graduated late.
I was like, plug it in. And I'm like, it was a school.
In 2019, or next year? Oh, you didn't take the whole year, I mean, that 1 year you do.
Well,
I just said that we just
Like, how far can that?
in terms of the two classes you get. And then in the summertime, I just gotta take 2 classes. You all right? That's good. Only gotta take 2 classes.
yeah.
Then you could take a lot of classes. Mind.
But at least you know, the other class was your writing.
Okay, perfect.
I was clicking okay and it was bringing me back and I'm like, that's not right.
You wanna take the class again?
Thank you.
And when I get home, this is.
We did.
I can imagine, every since you told me that picture, she was so adorable. I thought you might say, what did he ask about my brother? It's so pretty.
So that's what you do there?
Yeah. No, you can fill out that form. And then like, so serious because I no, because at the end you learn to get the actual.
She only watched.
But now, her father said that I want to sometimes can't use yeah. I think that like,
No, but I think
You watched up there.
That's so cute.
well, then it's actually
but I'm not worried.
No, but you don't want to, they don't want to be ready. Vegas, my daughter can dance as always, and I was like, no, don't act like, yeah, I grew up one day. I mean, like, 12 days, like 5 months. Then I don't have to teach you nothing. She thinks that because you want to think, house chores.
and they won't
Get in
get
your room, like, act like somebody, and you don't work.
You got that email? Yeah, so you'll find it.
And then that's what
Once you go to community,
I love that over here. But that's not,
Yeah, and that's everything from her. And it's like she don't give me all that book. How you know? I said, well, I told her. Why you there? And I got game on TV. You know, even the Wii U. They can play with the girls, they can still play with the TV. They take it out. Professor,
Elite?
I know what happened.
Okay.
She had the wrong calculator.
She had the wrong calculator. She got her download.
What you did? I had to download another one that somebody told me, and I think it works better.
Okay.
Remember, you know me and that calculator, and the numbers?
Calculator is key.
Yeah, right. You know, years when I was in school in,
Yeah.
I was ready to say something I ain't supposed to say.
Yeah, I sometimes forget that, how important the calculator is, because I
Oh,
just
we never had
refuse
calculator
to.
in the 70s, in the times.
I mean,
We had it on the TV, we had, you see, we ain't had computers though, we had the little typewriter that you type in.
the beads thing?
Yeah.
No.
No, yeah, the typewriter my day, in my age.
What's the thing with the beads?
Abacus.
Abacus. All
That's
right,
the one, I saw her, she got a picture.
this is not it.
That's why I like to talk about my age, you see how we fucked it up. Oh, yeah, that ain't gonna take on me. My son will do that.
Yeah, I heard her.
He's really old. I was like, I don't look old, but I ain't old.
Yeah, I was talking about that the other day, though, because my boss was talking and I was like, no, they don't teach you how to do anything by hand anymore. Everything is like Excel.
We have
They're like, yeah, like, punch it into Excel. I'm like, well, whoever's about to have a computer.
Yeah, everything was in. Typewriter, clean, got that clean book. You know how you have to correct in a typewriter, you have to move up, get it right out,
And it's
close it,
even my
scroll it back down.
We didn't do that. That was only in 2016. So this is like
Yeah,
really recent.
no, you're really bugging out with this stuff
That
here.
everything is on.
You know, we had to go to the library, open up a book, do research, write it. You couldn't even make copies of it because the copy machine, you had the little light like.
All right, great. So let's take a look at this Excel printout on page 425. If you can see it up here, great. If not, you need to put it up on your book. I don't think this light's gonna work. I don't have one. That's kind of, do you like a little mood lighting? Okay. Maybe I'll play around with the mood lighting. So this is a regression that is attempting to establish the correlation between linking sites and downloads for app developers. So if you develop an app, an application, the question is how many downloads will your app get? How many people will download your app on their phone or their smart, their device? Well, someone said maybe that has something to do with the number of websites you put your app on. So how many websites you link your app to. And that makes sense, right? If you have more websites that your app is linked to, you would expect that app to get more downloads. So let's do a regression and see if there's a correlation between number of linking sites and app downloads. And let's look at 4 points of data. So we have 4 different apps, and for each of them we have the number of websites that app was linked to and the number of downloads. We put them on that scatter XY. We find a line of best fit. We find an equation for the line of best fit. We look at explained, unexplained, total variation, how close those dots are, what can we explain, what can we unexplain, what we can not explain. We have performance measures, and we have inferential statistics down here. So, first thing, what is the equation for the regression line? For the sample regression line, what is the equation? I'll give you a hint. It starts predicted value of y, which is, actually I write it out, so downloads. Alright, downloads. Downloads equals, what is the regression equation?
Is it A plus B X?
Yes. What is A? Yes. Do we have a number for the intercept? Yes.
440.
Alright, so number of downloads is 440
Plus 11.
plus 11 times sites, websites, times linked sites. Linked sites. Alright, so I go to some tech convention and I say to developer, how many websites is your app linked to? That web developer or app developer tells me my website is linked, my app is linked to 10 websites. How many downloads do you think that app received? Or how many times was it downloaded? 10 websites.
110.
550.
110 plus 440.
You're on the right track, but you're not there.
I'm sorry, what are the numbers again?
10 websites.
10 what? Link sites?
Yep.
10 link sites, 110 plus 440.
And
550 is correct, yes. 550. So you say to that app developer, I bet you had 550 downloads, right? And what does the app developer say to you?
Oh my God, you're so right.
Oh my God, yeah, you're right. You're right. I want you to be my business consultant. Alright, I want to invest in your company. Because you had the regression equation. Now, I'm going to explain these three things, and then I'll let volunteers explain these three things. So the first question is, how well does this regression line fit our 4 points of data? Well, to answer that question, we need quantifiable measures of the total variation from average, right? What's the average number of downloads? How much do each of these points vary from that? That's our total variation. Some of that variation we can explain with this regression equation. We can say, well, we would expect one of the apps that had a lot of downloads to have that many downloads because it was linked to so many sites. And there's another one that we would expect to have not as many downloads because it was not linked to very many sites. The other two we can't explain as much. So we have a certain amount of that unexplained variation. And in these numbers, the sum of squares, error, sum of squares, regression, sum of squares, total. Alright, that's the unexplained. So for the explained, that would be the explained for each point squared, add it all together, comes up to 60,500. Go through the same process, sum of squares, error, and sum of squares, total. So we're going to take those three metrics and we're going to put them together somehow to find these three performance measures. Let's start with this one, the R squared. Who can explain what the R squared is, what it is in this case? Chris?
Percentage of variations can be explained by a model.
Yeah, alright, so that's R squared, it's percentage of variation that can be explained by the model. We would typically like that to be as high as possible. But in some cases, actually, as Ron reminded of us, even though it's not high, it's still relevant, it's still important. What is it in this case? What's the R squared for this model? Yeah, I like where you're going, Roxanne. Let's go there in just a minute. But what's the answer? Somebody tell me the
Oh,
answer.
it's up there.
Good. Wait,
It might work.
what's the R squared, Amanda?
0.6.
Okay, so in your own words, what does that mean?
That means that the percentage of the variation is about 69%.
Percentage of the variation. I don't like.
The percentage of, that's being explained by the regression equation?
Yes, the percentage of the variation that's being explained by the regression equation is 69.1%.
Say it again, what you just said, variation of,
The percentage of variation that is being explained by the regression equation is 69.1%. Okay, so alright, that's good, that's better than 49%, but it's relative too. We could evaluate that further if someone else had a different model. If somebody else had a model that says, my model explains 90% of the variation. Alright, we might want to go sit in that person's corner, right? Because they have better information, they have a better model, maybe they could do, make us more money, I don't know. Because they have a better model. And the other thing is, well, we might look at the strength of that explanatory value. Even though it's low, we might say, all right, well, we only have one independent variable, linked sites, all right? So it explains 40%, but it's a solid 40%. So that's another way where we might, use some judgment in quantifying it. Great, all right, so that's R squared. R, what is the R? What is one thing we particularly like about the R? And what is the R in this case? Yes. It is just the square root of what, Alina? Plus, we'll get to we'll get to this next week, the adjusted R squared.
Oh,
We'll get to that next week.
okay.
Alright, so what is R? What's another word for R? Another term for R? And what do we particularly like?
Correlation
Residential?
coefficient.
Yeah, correlation coefficient,
You
excellent.
said R.
Excellent. What's one thing we particularly like?
It tells us whether the slope is positive or negative.
Tells us whether the relationship is positive or negative. So in this case, do we have a positive or negative relationship? Positive, yes. So more websites, we would expect more downloads. Positive relationship. Okay, and this standard error of the estimate, what's that?
Can we go back to R squared for a
Is that
second?
the unexplainable part of it?
1 second, we're gonna go back to R squared, Ron.
I'm sorry, the correlation coefficient.
Oh, correlation coefficient, R.
If you get that by taking the square root of R squared, isn't it always gonna be positive?
It is always going to be positive, so then you'll just look at the line and you'll say, is it positive or negative? Good point, though.
So you can't really go by the. You can't go by the.
You'd look at this slope, this 11. Is this 11 positive or negative? If this were negative 11
Oh, I
or negative 2, then you would know you need to put a negative side in front of R.
Oh,
It was a negative 11.
Good question, Ron.
Right, like the lower 95% of this, negative 11.4.
Okay, how about the standard error of the estimate? What is that? Yes, on average, how far away are the dots from the line, and how far away are they in this case? Yes, 116.2. What's the units? 116.2 what?
Downloads, is it downloads?
Downloads. Exactly.
So the standard deviation is 116 downloads
Yes.
per data point?
Average. That's the average distance. So of these 4 data points, their difference between that data point and the regression line is 116 downloads. So your actual downloads on average would be 116 different from my expected number of downloads that I would expect for it. Alright, good. So we got 3 performance measures. Joanne, question?
So I thought that was standard deviation, the definition she gave, because I thought I was gonna say that, but then I said, well, that's standard error, or is it the same thing?
It's technically called standard error of the estimate in this case, but it's like standard deviation.
Okay, so it's
Which-
the same concept.
Oh, it's the same thing,
Okay.
like standard.
Okay.
It get me confused when they're saying like standard. All right.
Okay, now it's different than the standard error that we calculate when we look at sampling distribution and sample stuff.
Right, yes.
That's standard error, that's,
Right.
But this is closer to
kind of the
standard
same.
deviation. This is close, because you're talking about how far it is from the average.
alright, it's called standard error of the estimate. But when you say standard deviation, the definition of standard deviation is the average distance of the data points from the data center.
Okay.
And standard deviation is just the broad general term for the average distance from each data point from the data center.
Right, and this is from the line. Each
Yes.
point from the line.
Yes.
So that's the difference.
Yes. I see another hand. Yes,
So just to clarify, R square is from 0 to 1.
yes.
R is from -1 to 1. And then standard error is any number,
Any positive number, I
any
guess.
positive number.
Yeah, yeah. All right, great. So those are some performance measures to get us thinking about how
R square is from 0 to 1.
much we like this line of best fit, how well it fits the sample data. Let's do some inferential statistics. So this slope of 11, this is just the sample slope. Question I have for you, what is this slope in reality if I had every single app and the downloads that have been received for all those apps and the correct information about how many websites they were linked to? What is slope of the true population? How could I? No, it's 11 in the sample. So what is it in the true population?
Oh. The same?
That's our best guess. You're right, that's our best guess, but what are we going to do before we say it's actually the same? What are you going to provide me with before, how are you going to quantify what you think the true population slope is?
Like B hypothesis.
Yeah, you are going to use a t-table. You're going to give me a confidence interval. Confidence interval. Alright, you're going to say, alright, this is 11, but that's just a sample. But you know what I have? I have something called the sampling distribution of the sample slope. That tells me the likelihood of any sample outcome and how confident I can be that my sample outcome is within a certain number of standard deviations of the mean. Okay, so let's do it this way. Alright, so I'm going to go, for my confidence interval, I'm going to go 11 plus or minus some amount. What are the two components in my confidence interval, plus or minus what?
The T.
The t, yes. The t times the standard error, standard deviation of the sampling distribution of the sample slope. Alright, what is the standard deviation of the sampling distribution of the sample slope? Alright, so this is, I guess this could be rewritten as this. Sample standard deviation of the sampling distribution of the sample slope.
5.2.
Okay, yeah, 5.2. Yeah, that's what it says. 5.2, yeah. 5.2. If I want to be 95% confident, what is my t value? I'll give you a hint, it's not on that. You're going to need to look it up on the table.
I don't know what it means.
Oh, my.
The book, I'm just looking at this stuff up there.
So we're looking at 0.5 minus
What's that?
how many degrees of freedom?
Yeah, n minus 2 is degrees of freedom.
So we said 5.
Oh, so is it 4 minus 2?
Yeah,
Are we using the observation? That's our number.
Yep.
Okay.
4 minus 2 is your degrees of freedom.
So it'll be what, 0.05 on the T table and 2 degrees of freedom?
Alright,
95 confidence, so it's 5%. 0.5.
Four point three oh three? I like 4.303. 4.303 times 5.2. Alright. So, everyone understand how we got 4.303?
No, I'm choking. For nuts.
Alright, so we want to go plus or minus some number of standard errors. We're going to determine how confident we want to be, and that's going to determine how many standard errors we go plus or minus. If we want to be 95% confident, that means we're going to get it wrong 5% of the time. 2.5% of the time we're going to be too high, 2.5% of the time we're going to be too low. So we now need a t-distribution with n minus 2 degrees of freedom, and we have 2.5% in either tail. N minus 2, in this case, is 4 minus 2, because our sample size is 4. So we have 2 degrees of freedom. So you look on that t table, 2 degrees of freedom across 0.025, and you see 4.3.
Where do you see that? The T table. On the side? Oh,
Degrees of freedom, so this one is n minus 2 and n is 4.
Okay.
4 minus 2 is
Everybody good there?
right.
Alright, so what do we get for our margin of error here? What's 4.303 times 5.2? 22.3756? Alright, so 11 plus or minus 22.3756?
The first part is
33.37?
5, 6.
Both of them.
That's one. Just 11.
How much?
Negative 11.
Yeah. 11 minus 22,
I thought negative.
Oh, it's 11 minus.
Oh, right.
negative 11.37. Alright, excellent. Who would like to do the interpretation? It starts with I am 95% confident.
They say come, oh, that's 11.
Go ahead, Mandy.
The true population slope is between negative 11.37 and 33.37.
Exactly. Ron is 95% confident that the true population slope is between negative 11.37 and 33.37. Alright, what do you think about that confidence interval? Does it make you feel confident in this model? No. Kelsey says no? Why do you say no?
They're far off.
They're far off.
So it's like, it can fall in a lot of places between those two numbers.
Alright, it could fall in a lot of places, but although we can't really get caught up on the scale, because this is really only 44 units of difference. I mean, that could be a big number, small number, we don't really know. But there's something we really don't like about this confidence interval.
Could be positive or negative.
It could be positive or negative. What does that mean? Well, it means, first of all, it could be 0. 0 is within this confidence interval. So if we have a slope of 0, that means we have no correlation, no predictive ability. So we just wasted our whole summer by trying to build this model to determine the correlation between linked sites and downloads. Maybe we didn't waste our whole summer, we probably learned something, but we can't use this model to predict anything or explain anything if the slope could be 0. The other thing that's bad about it is that we're saying it could be negative and it could be positive. So I want to come to you and I want to say, hey, if I link my app to websites, will I get more downloads or less downloads? What are you going to tell me?
I don't know.
I don't know.
I can't tell you. Maybe you'll get less downloads, as many as 11 less per website you link it to, or it could be as many as 33 more for the website you link it to. Alright, do you see these two numbers anywhere on the Excel printout?
Lower 95 and upper 90.
Yeah, right there.
I'm good.
What do you think about that?
Right.
That's our 95% confidence interval for, this says big beta, big B, true population slope. We could also do a 95% confidence interval for the intercept. We don't care as much about the intercept, that's just a number that's math. We care more about the slope of the regression equation. Right. Let's do a hypothesis test. What do you say? Why not? Alright, let's do a hypothesis test. What is our key hypothesis test that we are most interested in? Determining whether or not the true population slope is 0. Now with our confidence interval, we already think we have some information about that. And I'll give you a hint, that is pretty much rock solid. That's going to tell us the same thing as our hypothesis test is going to tell us. But let's just go through the motions with the hypothesis test anyway. Null hypothesis, the slope is equal to 0. Alternative is no, the slope is not equal to 0, and we actually have something useful. Let's do a significance level, 5%. All right. Let's set up our rejection region. All right. So this is the sampling distribution of the sample slope. Right. If the null hypothesis is true, the true population slope equals 0. A little bit less or more, fine, but a lot less or more, that's when we think we can reject the null and maybe get something useful. If our significance level is 5%, how much area is in each of these tails? 2.5 in the upper rejection region and in the lower rejection region. Yep. What are our critical values there?
4.30.
Yeah, we're going to use critical values on a t-distribution with n-2 degrees of freedom. Critical value is the same as it was for our confidence interval, 4.303 and negative 4.303. We are ready now to calculate our test statistic. I'll give you a minute because you're all looking down. So this is how we set up our hypothesis test. Let's get that test statistic. All right, that is our t-stat. What is that? How do we calculate that? What's that equal to? B minus 0. Our sample slope of 11, we want to know how different that is from 0. Particularly, we want to know how many standard errors of difference it is.